So today we're looking at Thevenin theorem. Well, the Thevenin theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source called VTH in series with a resistance RTH, where VTH is the open circuit voltage at the terminals and RTH is the resistance at the terminal when independent sources are turned off. Sorry, there's a sources here are turned off. Okay, so that's about that. Let's look at the steps to Thevenize the circuit now. Well, the first thing to do is to remove the load resistance. That is the resistance you are asked to calculate the current that is flowing through it. The next is to calculate the open circuit voltage. When you remove the resistance, that place becomes open. The open circuit voltage, calculate the voltage across that open circuit. And the next is to compute the resistance as looked into from these two terminals after all voltage source has been removed. So we remove all voltage source, that is by short circuiting it, and the current sources are being removed by open circuiting them. So the voltage we get is called Thevenin voltage, and the resistance we called is called Thevenin resistance. So we then replace the circuit again by the Thevenin voltage in series with the Thevenin resistance, and then our load resistor is placed back, and then we calculate the current using this formula that IL is equal to VTH over RTH plus RL. Let's take an example now. So look at this first question. Obtain the Thevenin equivalent circuit and calculate the current flowing through the 15 ohm resistor in the circuits below. The first thing to do, look at the steps here. First, to remove the load resistance. And remember, the load is that resistor. You have to calculate the current flowing through it, and that's the 15 ohm. We remove it. And then find the open circuit voltage, which appears across the two terminals where the resistors has been removed. So this is what we have to do for step one. So I have removed the 15 ohm resistor, which is the load resistance now. Now, here we have 3 ohms, and here we have 12 ohms. And then this is 24 volts. Okay? Now, I will look for the open circuit voltage, VOC, or you call it VTH, Thevenin voltage. To get that, we can use the voltage divider rule. And why am I using that? As we look at the question now, current is being supplied by this cell here. And when the current flows to this junction or this node, it divides. Some go here, some go here. That tells me that 12 ohm is in parallel with 15 ohms. And in parallel parts, the voltage is the same. So the voltage across the 12 ohm resistor is the same as the voltage across the 15 ohm resistor. And so right here, the voltage across the 12 ohm is my VTH. But as you look at this circuit now, no current flows here now because it has been opened. Then this is a series circuit. You can use voltage divider rule there. So our VTH is the voltage across the 12 ohm resistor. And using voltage divider, we're using voltage divider rule. We can say the voltage across this 12 ohm resistor is 12 over the two resistors sharing the voltage, which is 12 plus 3 times the voltage they are sharing, 24. And this will give us 19.2 volts. Another way to get our VTH is to get the current in this series resistor. That current there is the voltage over total resistance in that series circuit. And that voltage is given as 24. So that's the voltage here. All over, the total resistance is 3 plus 12. This is going to give us 1.6 ampere. If you get a current flowing in that circuit now, then you can calculate your voltage VTH, which is the voltage across the 12 ohm resistor. And that will simply be IR. the current across the 12 ohm resistor times the 12 ohm resistor itself, the resistor itself. So this will be IR. What's my I? The I is the current you've gotten since it's a series circuit, same current flows through it. Then times the resistance, which is 12. And you still have 19.2 volts. So that's how to get your VTH. So that's good for step 1 and step 2. Now the next step is to compute our Thevenin resistance, compute the resistance of the whole network. To do that now, what do? We say we remove all voltage sources. After all voltage sources has been removed, so we redraw this, but now we've gotten our VTH. To get our RTH is what we want to do now. So we redraw that, but remove the voltage source. Okay, we short circuit it. Our 3 ohms being here, and our 12 ohm being here, and this part being opened again. 12 and then 3. So now the next thing is to look. That's what instruction is. Say, as look from these two terminals. From this time I'm looking at here, I'm going to see how these two appear to be. Well, looking, some say it appears parallel, but I don't like using that principle. I just simply assume that current is being supplied, which is not true, from this part, and when the current gets here, it is split. So if current splits across two parts, then that part is in parallel. So this whole part is in parallel with this part. So we can say 3 ohm in parallel with 12 ohm resistor are the only resistors we have here. So, and then in parallel, that's my RTH. We sum up the two resistors. So that will be our RTH being equal to 3 ohm in parallel with 12 ohm. Again, I would like to say there's a fast way of getting the total resistance here, and that will be product over sum. If you have two resistors in parallel, only two resistors, it doesn't work for 3 resistors in parallel. This will be 3 times 12 product over sum. 3 plus 12. That will give us 36 over 15. So that's that about that. Now, mind you now, another way to do this is to have said 1 over RTH is equal to 1 over 3 plus 1 over 12. But you have the same answer we have here. So that's that about that now. Now, the last thing to do is to draw our Thevenin. That's the step 4. Draw our Thevenin equivalent circuit. So Thevenin equivalent circuit look like this. Our VTH, our RTH, and our load resistance. Your VTH, your RTH, and your load. So our VTH, we got that to be 19.2 volts. Okay? The next thing now is to get our RTH, which is 36 over 15. This should give us 12 over 5, which should be 2.4 ohms. That's what we have there, 2.4 ohms. And then our load is that one we removed initially, which is 15 ohms. So now we can now calculate our load resistance. This is a series circuit, and the series circuit is the voltage over total resistance there. So our load resistance, our load current, sorry, which is what is required. The first thing required is to draw Thevenin equivalent circuit. These are Thevenin equivalent circuits. The next thing required is to calculate our load current, which will be total voltage, which is VTH from that formula there, over total resistance, which is RTH plus RL. Our VTH is 19.2. All over our RTH is 2.4 plus 15. And this will give us about 1.1 ampere. That's that about that. Example, we have to calculate we have to obtain the Thevenin equivalent circuit and the current flowing through the 8 ohm resistor. Well, quite another easy question. The first thing to do here is to remove the load resistor as usual. So this is going to be And we calculate this is the resistor we remove. So I'm looking for the VTH now. It's 10 volts, it's 4 ohms, and it's 5 ohms. Now understand, as look at the original question, these two are in parallel. Why? Because this is the current provider. When I'm looking for my VTH, I go back to the current provider or the voltage source. Look at this now. Current coming from this, we get here and it split across these two resistors. So these two are in parallel. You see, the voltage, the open circuit voltage here is the voltage across the 5 ohm resistor because voltage in parallel are the same. So very easy now. My VTH is simply going to be the voltage across the 5 ohm resistor, which is using voltage divider rule, which is 5, over the two resistors sharing the voltage, 4 plus 5, times the voltage that they want to share. So this is simply going to be 50 divided by 9. So this is 5.56 volts. Now the next thing is to get our RTH. We are going to deactivate the voltage source. So this is going to give us so we've deactivated the voltage source now. Again, like I said, I don't like using the principle of looking. This is 4 ohms and this is 5 ohms. What I will simply do is to say, assuming current is coming from this open part, when the current flows and get to this junction, some will go through this 4 ohm resistor, some will go through this 5 ohm resistor. That makes these two resistors to be in parallel. And then I can say my RTH is simply 4 ohms in parallel with 5 ohms. And that's just all. Again, use our easy method, product over sum. That is 4 times 5 over 4 plus 5. This will be 20 over 9. And 20 divided by 9 will give us 2.2 ohms. So we've gotten our RTH and we've gotten our VTH. Next is to calculate, to get our Thevenin equivalent circuit. And that's going to look like this. With our VTH here, with our RTH here, and with our load resistor here. Our VTH, which is 5.56 volts. Our RTH here, and our RL. Our RTH is going to be 2.2 ohms, and our RL is going to be 5 ohms. So VTH, we can say our load current, which is the current across our load, like I said, it's a series circuit, is going to be VTH over RTH plus RL. Our VTH is simply 5.56 all over RTH 2.2 plus 5 ohm for the load. And this is going to be 5.56 divided by 2.2 plus 5, 0.77 ampere. Example 3. Use Thevenin's theorem to calculate the current in R using the figure below. Okay? So, solution. The first thing, let's get our VTH. And that will look like this. So we remove the load resistor now. So I'm looking for the voltage, the open circuit voltage here. So this is 5 volts, 3 ohms, 14 ohms, 5 ohms, and 9 ohms. Okay? So actually, the VTH is the voltage across the 9 ohm resistor, because if our zone current is coming from here, when that current gets here, it's going to split into two. Some goes into 14 ohm, some goes into 5. The one that goes into this 5 ohm, we get here and split again. And so these two parts will be in parallel. The one that goes here will come here and split. Some current will come, some current will be here. So these two parts are in parallel. So VTH is the voltage across the 9 ohm resistor. How do we solve this? Because this is not a series circuit where we can just use the voltage divider rule. No. Assuming it's a series circuit, in the previous question we solved, when we are calculating our VTH, we realize we have a series circuit and we use voltage divider rule. So other principles can be applied there. We can apply the Kirchhoff law, we can apply the mesh analysis, superposition, or whatever, and calculate our VTH. But I prefer using mesh to do mine. So I will assume we have two mesh here now. This is mesh 1, called I1, and this is mesh 2, I2. I just want to get the I2. If I get the I2, I've gotten current flowing through 9 ohm. Use that current and multiply this 9, and you will get your VTH. So doing that now, this is simply going to be using mesh. For mesh 1, we are going to have 5 minus 3I1 minus 14 into I1 minus I2 being equal to 0. So simplifying further will give us 5 minus 3I1 minus 14I1 plus 14I2 equal to 0. So this will give us 5 being equal to 17I1 minus 14I2. This is my equation 1. Then for mesh 2 now, we are simply going to have minus 14 into brackets I1 minus I2, minus I1, then minus 5I1, I2, minus 9I2 equal to 0. So this is going to be minus 14 I2 plus 14 I1 minus 5 I2 minus 9 I2 equal to 0. So it's going to be 14 I1 minus 5 minus 14 will give us minus 19. Minus 9 again, that minus 28. 28 I2 equal to 0. So this is equation 2. So simultaneously solving equation 1 and 2. Solving equation 1 and equation 2. And that will give us 5 being equal to 17 I1 minus 14 I2. And then 0 being equal to 14 I1 minus 28 I2. Equation 1 and equation 2. So if we solve, we get our I1 actually is equal to 0.5 ampere. And the I2 will be equal to 0.25 ampere. So the next thing to do is to get our VTH. So our VTH, since I've gotten I2, and that's coming flowing through this 9 ohm resistor, I can say my VTH is IR. The I is the I2, which is 0.25, and the resistor is just 9. So this is going to give us 2.25. 2.25 volts. The next is to get our RTH. We're still going to use that, but short circuit is in the voltage source. So we're looking for our RTH now across these two terminals. This is 9 ohms, this is 5 ohms, this is 14 ohms, and this is 3 ohms. So the first thing to do here, I said you assume current is coming from here. It's an assumption. When current gets here to split, some will go in here and some will go in here. These two are supposed to be in parallel, but that's not the last resistors we have. As you stretch the current going in here and that one gets here, the current that splits to this 5 ohm will get here and split again. Some will go in here, some will go in here. That means 3 and 14 are in parallel. So first of all, 3 in parallel, 3 ohm in parallel with 14 ohm. And that will give us 3 times 14 over 3 plus 14. So this will give us 42 divided by 17. And that's 2.47 ohm. If you combine these two, this will automatically look like this. Where these two combined give us 2.47. And then this 5. So this is going to be this in series with this. This 9 ohms. So 5 in series with 2.7. Because the current is coming from here, some will split here. The one that splits here will go like this. So same current that flows through 5 ohm flows through this 2.47. So our resistance for these two will be 2.47 plus 5. And that will give us 7.47 ohms. Now, this will be withdrawn in this manner. This is 9 ohms and this 7.47. So our RTH. So RTH is simply these two in parallel, because when current comes from here, some will split, some will go here, some will go here. So these two are in parallel. So our RTH is going to be 7.47 in parallel with 9 ohms. And this is simply going to be 7.47 times 9 divided by 7.47 plus 9. This is 4.082 ohms. So the next thing is to draw a Thevenin equivalent circuit now. These are VTH, our RTH, and the load. Our VTH, we got it to be 2.25 volts. That's what we did there. Our RTH was 4.082, and our load was the 1.5 ohm we removed. So simply, our current across the load, since the series circuit is going to give us VTH over RL plus RTH. VTH 2.25 all over RL 1.5 plus 4.082 ohms. So this will give us 2.25 divided by 1.5 plus 4.082, 0.403 ampere. So that's our answer for this question. You can try the following exercises and their answers are given alongside.